All right, last time we started our discussion of inverse functions, and specifically what we had already talked about so far was functions that are one-to-one. So one-to-one are functions that have this nice relationship that every input has exactly one output. There's this sort of a one-to-one pairing. And you guys know what you mean by one-to-one, right? So you could think about it like a marriage relationship, one husband, one wife. That's the way we're supposed to go with that, right? Absolutely. So it's kind of like that. We talked about the horizontal line test and how it was very similar to the vertical line test, just horizontal lines. And it doesn't necessarily mean it's not a function. You can definitely have a function, but it's just a specific type of function. Is it one-to-one? And we had talked about that inverse functions, generally speaking, are switching the x's and the y's and solving for the new y. But we hadn't done an example. So that's where we're going to pick up on today. Example number 2, which is we're going to find some inverses. So the thing to keep in mind and to remember is that f of x is just another way of saying y. So the equations that we're given are going to always be given as y equals already. So this really says y equals x over 2. So to switch x and y would mean that I would now write x is equal to y over 2. Okay? Just change where the x is and change where the y is. And then I'm going to solve for the new y. So if I want to solve for y, what do I need to do with that 2? Yeah, I need to multiply it on both sides. So now I have 2x equals y, or I can write y equal 2x. And what you generally see or requested at the end is for you to write it with the inverse notation. Now I didn't mention that over here. It was there. I just didn't make mention of it. The inverse notation looks like it's got a -1 power. It's not a power any more than those parentheses mean multiplication. It's another one of those really awful things that we do in math where we give something a meaning and we say, oh, except when it looks like this, and then it means something different. But let's be honest, English is like that too, right? It is. You use words and they mean something different, even if they're spelled the same sometimes. So this is one of those things. This middle notation means it's the inverse. And again, it's just notation. All it means is that at the end, we rewrite it so that the y is replaced by this f inverse notation, and then it's 2x. So very truthfully, this is nothing new. The only new thing about it is the notation, where at the end I write f inverse, and switching x and y, which is not a new concept. We just haven't actually physically done it with these equations before. So on the second one over here, again, this is y on the left-hand side. That's what that means. And if I switch x and y, now I'm going to say x equals the cube root of y minus 9. Okay, so one of the things you can think about when you think about inverses and solving them, because we're about to solve this one and go the other direction, is it's very much like taking directions on like Google, where it tells you this is how you get from point A to point B, and then you want to go in reverse, right? If you want to get from point B back to point A, you just reverse all the directions. You just do everything backwards. So we're going to do the same thing for solving this. We're going to undo all the operations. So right now, how do I undo a cube root? You cube it, right? So I'm going to undo my cube root by cubing. So now I have x cubed on the left, and I have y minus 9 on the right. And then how do I undo subtraction of 9? You add 9. So now I have x cubed plus 9 on the left, and have y on the right. And we sort of have this tendency to want it to say the y on the right-hand side, right? So if that's you, just rewrite it. If you don't care, I don't care either. You could leave it and it'd be okay. But the last thing you're going to do, either of those versions, is to change what y says to say f inverse. Okay, any questions on either of those? Got a couple more, but okay. All right, so let's try another one. This one's messier. And in particular, it's messier because there are x's in multiple locations. That makes it harder. It does. The process is still the same in terms of solving and so forth. It's just messier. So again, this equation is y equals. So I'm going to change my x's and y's. So somebody tell me what you're going to write down for the next step. How's it going to start?
I know this sounds stupid.
It's okay.
What is even the point of having this f of x if we're just going to put in a y? Why
It's-
not just do it this way?
It's notation that allows us to evaluate things in a simpler way. For example, if I have this notation, f of x equals whatever, and I want to say that x is equal to 3, right? What this allows me to do is to write f of 3, which will then have the 3 replacing all of my x's. So it's a notation that's telling you, number one, you have a function, because that matters, because you can always have y equals, and it's not necessarily a function. So it tells you it's a function, and it also gives you a nicer way of communicating what you do when you evaluate it at numbers. Now, why we have it right here is because that's the problem and how it's given to us. And in order for us to actually process through, we don't even really have to sort of what I'm doing where I'm circling it and changing it to y. I'm just trying to get you guys to remember every single time that it really is the same thing. It's just talking about y values. Equivalently, if we think about our x and y axis, you could call it, for functions, the x-axis and the f of x-axis. You could call it that, and it would be okay. We just tend to go with the alternative of y, because it's more general. So what's going to be my rewriting step for this equation? What's it going to look like? How about x equals to start with? Right? I'm just switching the variables, x equals. And what's the other side going to look like?
Y plus 3 over y minus 5.
Thank you so much, Aspen. Yeah. You may not know how to solve it, but you should be able to rewrite it okay. You're just changing x's to y's and y's to x's. Solving this one's messier. Now, keep in mind that it's going to always be easier to not have a y or an x or whatever in a numerator and a denominator, right? So the first thing we're going to do, and the first thing I generally do for a lot of problems, is let's get rid of the denominator, right? Denominators are not super friendly, so if I can change it, we kind of like to. So we're going to multiply both sides by y minus 5. Now the whole point of that is that if I multiply by y minus 5, I can cancel those, right? That's the point. So on the left, I can distribute. So now I have xy minus 5x. And on the right side, I have y plus 3. Okay, is that all good? Is that step all right? Okay, so that's good news. What I need to do now is, again, the goal is to solve for y. So solving for y means y can't be in the denominator, so the first thing I did was get the y out of the denominator. So that's good. But now I need to solve for y. Well, it means that the y's have to be the same side. And right now they're not, right? That's what happens anytime I try to solve for something is I need all of the pieces that say y in them together. They need to be grouped. So I'm going to move the 5x away to the right-hand side. So right now that gives me xy on the left and y plus 3 plus 5x on the right. Okay, so that's shifting the constant or the coefficient variable combination 5x away. And now I'm going to shift the y over onto the left-hand side, like so. So now I have xy minus y equals 3 plus 5x. Now this is not finished, but it's a really good point in the process because everything with y is on one side and everything on the other side doesn't have y in it. So I'm sort of separating or grouping like terms. I'm grouping everything with, the x's on one side, not x's, but the y's on one side, and I'm grouping everything without them over there. Okay? But the thing is that now that I have everything that's grouped on the left has a y in it. Sorry, hang on, I'm trying to give myself some more space. Everything over here has y in it, right? So one of the things that we've learned when we have been solving like quadratic equations is that if there's things that are alike, you can factor them out. Do you remember that? Factoring. Everything has a y in it, so I can factor the y out. This doesn't affect the right-hand side at all. But if I take a y out of xy, what am I left with?
X minus 1.
Yeah, I'm left with the x, and then Yana actually continued on for me. She's right, it's minus 1. So remember, when I'm taking things out, factoring them out, it's like division. What I'm really saying is if I have xy and I divide by y, what do I have? Well, I have x. And if I have negative y and I divide by y, what do I have? Negative 1. Okay? So then I've got y. I've got things that don't have y equals all the stuff that doesn't have y. And these two pieces are multiplied, right? So how do I get rid of the piece that's multiplied by y? You divide, right? So I'm going to divide by x minus 1. So y is actually equal to 3 plus 5x over x minus 1. And what's the last step? Write the f inverse, you're right. So f inverse of x equals 3 plus 5x over x minus 1. Those are the hardest ones. The rational ones are the hardest ones.
So do we not have to find domain and range?
Not right now. So we could find domain and range, and we are going to talk about domain and range. So it's very interesting. So domain is x values, right? And your range is y values. So if you're switching your x values and the y values, what do you think is going to happen to domain and range? They're going to switch. Yeah, they are, because that's exactly what's happening. So you've actually hit on a very good point, and we actually will talk about it as well. I can't remember if it's in this lesson or a little bit later. But if you were to take a look, this is a good example of one. So let's just do it right here since you've mentioned it. We know right here that x cannot equal 5, right? So in this domain, x can't be 5. And in this equation over here, this x cannot be 1. Agreed? So what that actually tells you is actually a lot. It tells you that the first equation, right, for f of x, that it has a, actually let me do it like this. It has a domain where x is not equal to 5. And for f inverse down here, its domain is that x cannot equal 1. So if I want to find the range now, back up here for f of x, it's going to be y cannot equal 1. And I've done here, if I'm finding the range for f inverse, it's going to be y cannot equal 5. Because x's and y's are just switching. So it's actually really easier, to be honest, to find the range by looking at the domain of the inverse, because we've got those denominator issues going on, right? Denominators cause problems. They always do. And so I can identify the problems easier in that form than otherwise. So I'm glad you asked that, because that'll save us time somewhere else that I won't have to talk about it. So it's good. All right, I have one more example of the inverses. Okay, so on this one, this is y, right? Just like we've been saying all the way along. So how will I rewrite this equation? Be bold. X equals, right? And then what? Yeah, Melissa wants to talk, but she just doesn't want to sound very loud. Yeah, you just plug them in as y's. So x equals 1 minus y squared. It's actually really important to notice that they've given us a domain on this to begin with, and it may feel a little bit funny, but let me actually show you why they did it. If you take a look at this equation, if you graphed it, your calculator would show you this. and you actually graphed 1 minus x squared, it would look like this. And if you think about this, when we talked about it last time, I told you, you can only have an inverse if the graph is 1 to 1. Is this graph 1 to 1? It's not. It fails the horizontal line test, right? It fails. So what happens when they've told you this x is greater than or equal to 0 business is they've eliminated half the graph. So it's like in essence they've done, in essence they've done this to the graph. And when they do that, now it's 1 to 1. Because that's why they did it. That's why they told you x is only greater than or equal to 0, is because if they didn't, you would actually be finding something that's not an inverse. You probably wouldn't even realize you did it along the way. It would have been an accidental sort of thing. But you wouldn't have actually found an inverse. But if they eliminate half the graph so that it now is 1 to 1, as you do the algebra on the way through, what you're finding actually really will be an inverse. So that's why they did it. Okay, so let's take a look at solving this. So the goal is to solve it for y. So we move from the outside in. On the outermost side is this 1. How do I move the 1? You subtract it, because right now it's added, right? So if I subtract my 1 from both sides, now I have x minus 1 equals y squared, negative y squared, excuse me. And then what? Everything is just a little bit crunched. The goal is to solve for y. So am I going to deal with the negative first or the squared first? Nope. I'm going to do a square root in a minute, but first I got to get rid of the negative in front of it. So the first thing is I need to get that negative to go away, so I'm going to divide by negative 1. So these two negatives end up being a positive. Now what that really does is this makes it negative x plus 1, or you could write it as 1 minus x if you wish. And on the right-hand side, I now have y squared. And just like you said, Logan, I can take a square root now. Now, normally, when I take a square root, I have to put a plus or minus. So let me put that on here, and let's think about whether or not I actually need to here. Here's where I was going to talk about domain and range. So we've already addressed it, so it's really good. But now we're addressing it from a standpoint of a square root. So if this domain is x is greater than or equal to 0, then when I switch everything, it tells me that this new range for y is that y is also greater than or equal to 0. So down here, I know that y is greater than or equal to 0. And I'm going to write it in just so you have it in your notes. It's because originally x was greater than or equal to 0, and I switched to the x and the y. If I switched to the x and the y, and before x was greater than or equal to 0, then now y is greater than or equal to 0. And what that means is that I don't need the plus or minus. I'm only getting the plus part, because this y has to be positive. So my equation is y equals the square root of, you can do 1 minus x squared or negative x, 1 minus x or negative x plus 1. And if I write it in inverse notation, then I get the square root, f inverse of x equals the square root of negative x plus 1. Now there's this very interesting relationship of doing and undoing each other, right? We talked about how do I undo this cube root, I cube. How do I undo subtracting 9, I add 9, right? How do I undo multiplying by negative 1, I divide by negative 1. So there's actually more to it than that that's a little bit more specific. F and G, or f and f inverse, if you want to call it that, the two functions are actually inverses if they have this very interesting embedded relationship. And we've talked about this in the last section. We called it composite functions. So if f composed with g is x and g composed with f is x, then the functions are inverses. we did that in the last lesson, this idea of composite functions. So that's not new information. The new information is that if it has this very special relationship that it equals x once you do it in both directions, then the functions are inverses. Okay, so we're going to try it. So we have to test both directions. I have to test F composed G, and I have to test G composed F. Okay, so I've got two problems here. Now, the way that we did this last time is we said, okay, we're going to start on the inside. What is G of X? Well, let's see. It's negative 0.2x plus 4, right? That's G. And then we said, okay, now we're going to take that G of X and we're going to stuff it in, plug it in, evaluate it at whatever you want. Everywhere in the F equation where there was an X. So I have 20 minus 5. And then previously there had been an X there. Right here. So over here where the X had been, I'm going to put in what I'm replacing it with. Whoops. So this quantity substitutes in for X. And then we simplify the algebra for it. So on this one, that means I'm going to distribute. So I have 20 minus. 20. And then I have negative 5 times negative 0.2. Do you know what that is? You know what the sign is. What's the sign? Positive, right? Okay, so what's 5 times 0.2? It's 1. It is, yeah. So 1x, or you could just write x. And then I have negative 5 times positive 4, which gives me what? Negative 20, and then what do you see happening? Yep, positive and negative 20. So this leaves me with x. So I stand a good chance at this being an inverse. Half of it worked, right? Now, typically speaking, that means we're going to expect that the other half's going to work as well. It's more of a check step kind of thing. We're not expecting anything different, but we do need to check it. So, again, we write down what does f of x equal now? Well, f of x is 20 minus 5x. And then we are going to take that f of x and we're going to stuff it in, evaluate it at the x in the g equation. So that equation was 0. Okay, I just need to shrink the other side. That's what I need. Give myself a little more space. Better. 0.2, okay? And then x is where it was next. Well, my x is 20 minus 5x. And then I have plus 4. Okay? So again, this ends up being evaluated into where x is. And now I have algebra to simplify. So I have negative 0.2 times 20. What is that? Well, it's negative. What's 0.2 times 20? It's 4. So I have negative 4. And then I have the negative 0.2 times negative 5x. Well, negative and negative is a positive. We already did 0.2 times 5. What was it? 1. So I have 1x again here. And I have the, was it minus 4 and I wrote it wrong? Oh, no, it's plus 4. I have negative 4 at the beginning. So I have plus 4 at the end. And lo and behold, what happened? Y'all aren't excited at all. The 4 is canceled. but we kind of thought they were going to, right? I mean, so that's why we're not excited, right? I'm sure that's what it is. Yeah, it worked in both directions, so these are inverses. It works. So let's do the process again with some different functions. These were linear equations that we saw. Now I have one that looks like it's not linear. It actually is. It just has a different form because it's fractional. So we're going to do the same thing. F compose G of x. So G of x is 5x plus 3. And then I'm going to take that and I'm going to put it into my F equation. Well, my F equation has an x at the beginning right here. So that x will be replaced with the 5x plus 3. And then it has minus 3 and over 5, right? So this piece right here replaced my x. Beautiful things happen there, right? What do you cancel first? The 3's. Positive 3, negative 3. So what I would have if I wrote this step out next is I have 5x over 5, which is what? X. So this is actually a little bit easier because I don't have the decimal multiplication to do. Now I have to go the other direction, g of f of x. So f of x is this fraction, x minus, is it minus? Yeah, minus 3 over 5. And then I'm going to take that, I'm going to put it into the g equation. So the g equation has a 5, and then it has x, but my x is now x minus 3 over 5, and then plus 3. So again, this is replacing the x in that equation. That's what you're seeing happening. And again, beautiful things happen. What cancels first this time? The 5's. And again, if I wrote out a simplified version at this point, it would actually say x minus 3 plus 3. And then what would cancel? The 3's. And I'd be left with x. And we would say, yes, these are inverses. No problem. One more example and we're done with this lesson. And then we'll start 3, what are we in chapter 2? 2? Yeah, 2:6. Okay, so last example for inverses. Okay, so now I have f of x is x over 2, and I have g of x is 3x. So we'll do f of g of x by starting with g of x because it's the inside function, which is 3x. And I'm going to plug that in. For x. The x is in the numerator all by itself, so now my 3x is where the x previously was. Kayla's shaking her head. I had to show you one that didn't work, right? I mean, it just doesn't equal x this time, right? It just doesn't. This does not equal x. It's still 3/2 x, or 1.5x if you want to write it that way. It's not x. And it's enough right there to say that they are not inverses. Now, if you wanted to verify it going the other direction, you could do that too. So let's do it just so that we can see what it looks like more than anything. So my f of x equation is actually the x minus, or x over 2. And if I put that into g of x, I would have a 3 times the x over 2, and lo and behold again, still not x. It doesn't always work. So there's a very unique relationship. Every function has only one inverse, so there's plenty of functions you can compose it with that won't be its inverse function.